In this lecture, we're going to look at some applications of resonance structures, just so we can remind ourselves why these things are so important. So I'll just kind of lay out what the two approaches that I like are. I'm going to call them the best, and that is probably inaccurate, but they're two popular reasons why you want to study resonance structures. So the best use of resonance structures includes, let's just put includes, right? Then I can cover all my bases. So one, understanding aromaticity. And number two is understanding relative acidities, or really predicting relative acidities. Looks good. Okay, so let's start with aromaticity. And we're going to review what we talked about in organic chemistry too. So this is a special stabilizing property of organic molecules that are, now let's name those rules that are required to being aromatic. Can you remember them? Let's focus on the four major rules. Number one, we have to be planar, which is flat. Number two, we have to be cyclic, which means the system that I'm considering must be confined to a ring. We can have things hanging off, but those things won't be aromatic. The aromatic portion or piece of a molecule is always inside a ring. And within that ring, the electrons that we're considering must be conjugated. And you can think about conjugation at a basic level as alternating double, single, double. It does get to be a little bit more complicated in some systems, but we'll look at that. And then number four, we must follow Huckel's rule. So Huckel's rule is the 4n+2 rule, where 4n plus 2 equals the number of pi electrons in the flat conjugated ring. Okay, so the total number of electrons within the ring is equal to 4n+2. Now what I'm going to do is turn the page and we'll go through Huckel's rule just for benzene so we can warm ourselves up a little bit. So the 4n+2 rule is obeyed if n is an integer. Okay, so benzene. What we're going to look at is not the total number of electrons within benzene, but within that cyclic conjugated ring, we're going to focus on the pi electrons. And there are 6 pi electrons. Remember, pi electrons come from the lone pairs of electrons that are in resonance with the double bonds, or just the double bonds, and just the double bonds. So here we don't have any lone pairs to worry about. It's just the 3 double bonds. So the 3 double bonds provide each 2 pi electrons. So one double bond supplies 2 pi electrons along with 2 sigma electrons, but we don't care about those. 2 pi electrons, we have 3 double bonds, so that's 6 electrons total in the pi system. 3 times 2 electrons per pi bond, or over 1 pi bond. How about that? Okay, quick conversion factor. So there's 3 pi bonds, 3 times 2 then is equal to 6 pi electrons. Okay, so 6 is then equal to 4n+2. Now let's solve for n. N is equal to, well, we subtract 2, that gives us 4, n is equal to 1. Check. N is 1 is an integer. So benzene, with its 6 pi electrons within the flat conjugated ring system, follows and obeys Huckel's rule. So we would say that benzene is aromatic. It has all 4 attributes. Remember, if you have 3 attributes, but you follow 4n rule, you're considered anti-aromatic, and you will do something to violate the other 3 rules to avoid that situation at all possible. So in organic chemistry too, we spent a lot of time doing some practice where I said label the molecule as being aromatic or not aromatic. That's a pretty good skill for organic chemistry too, but it's kind of an awkward skill, if I'm honest, because often there are portions of the molecule that are within an aromatic ring, and there are portions that are just outside of the aromatic ring. So for example, if we say that benzene is aromatic, what about naphthalene? Naphthalene is aromatic. It's important to note that if one resonance depiction of a ring system is aromatic, the other depiction of a ring system is aromatic. So in this right-hand resonance structure, where all I've done is just moved the electrons in the right ring system around, okay, while the ring in this right-hand structure, while the ring on the right looks to be aromatic, this left one looks to be problematic, but in fact, it's still aromatic. Okay, and you can see that by looking at the resonance structure over here, where we have this natural benzene. And the double bond that's split in the center, sorry to get all these colors, this double bond that's split in the center of this resonance depiction is shared between both sides. So the fact that there's a shorter line on the left side indicating the double bond's position, that's just an artifact of drawing these things on paper. Okay, so I'd call that aromatic, and then this structure aromatic because it's a resonance structure of the other molecule. Now, where this problem starts to fall apart is if you've got multiple rings, 2 of which are aromatic, and then this top one, which I'll highlight in yellow, is actually not aromatic. So then is this overall molecule aromatic? The reason why it's not aromatic is we have 2 hydrogens and we've lost conjugation. So if I had to categorize this molecule, would I call it an aromatic molecule? Well, certainly we're aromatic in these 2 rings, we're just not aromatic in this ring. Okay, so aromaticity on multi-ring systems is kind of an awkward thing to propose. What you want to do is look at each ring individually and see if they're aromatic. That's pretty helpful. Okay, let's look at some more complicated examples where we've got, and by complicated, I mean, let's just introduce some non-carbon atoms. So nitrogen's kind of interesting because when it's inside the aromatic ring, the lone pair has a choice. It can be part of the pi system or not. I mean, it doesn't really have a choice, but you have kind of a choice. Okay, do we want to make this part of the pi system? Well, in this case, no. Why? Because if we ignore those lone pairs of electrons, we just have a benzene molecule where one of the carbons is replaced with nitrogen. That is 3 double bonds alternating. And so we could be aromatic that way. So this molecule will actually position that lone pair of electrons to sit in an sp2 hybrid orbital facing outside of the ring and not in conjugation. Okay, if you put non-carbon atoms off of a benzene, it's still aromatic. It's not very interesting. But if you introduce these non-carbon atoms inside the ring, in particular, when you've got oxygen with its 2 lone pairs of electrons, you start to get to interesting things. This molecule is aromatic where one of the 2 lone pairs is going to be part of the aromatic system. So maybe this one's not, but then this one is. Okay, so this is not part of pi system. Or maybe I'll do something clever here. I'll highlight part of the pi system in yellow, but then not in red. So the molecule is going to position itself where one of the lone pairs of electrons sits in an orbital facing outside the ring. The other one's going to be positioned perpendicular to the ring, but in conjugation with the other pi bonds that also sit perpendicular to the ring. So one's part of the pi system, one's not. That gets us to 6 electrons then. If you count the two double bonds, that gets 4 pi electrons plus 1 lone pair, 6 pi electrons total, which matches benzene. If we introduce both of them, somehow, some way, we get to an anti-aromatic system. Okay, so this next one, we can take advantage of these lone pairs of electrons, because those plus the other 4 pi electrons from the pi system will make this an aromatic molecule. Now, there's some complicated heterocycles out there, and maybe complicated is a strong word. What if we have something like this? Well, anytime you have nitrogen with its lone pair, and that nitrogen is directly kind of part of a double bonded system, it'll probably stick that lone pair outside the ring, because the nitrogen-carbon double bond is going to form a normal pi bond, and those pi electrons will be positioned already inside the ring. So what we're going to do is we're going to not count, we're going to position, the molecule is going to find a way so that the lone pair on nitrogen and one of the lone pairs on oxygen is not part of the pi system, but then the other lone pair on the oxygen is part to get us to 6 electrons total. So all of these examples so far have 6 electrons. And that's typically where you see most aromatic molecules. I think you get the strongest aromatic stabilization from a 6 pi electron system. Okay, so aromaticity resonance is helpful for understanding aromaticity, because we can look for resonance structures. If it's hard to see aromaticity in one resonance structure, you can consider an alternative one. Okay, now another thing I said that resonance can help us with is predicting relative acidities. So it turns out that you can use resonance structures to show aromaticity when lone pairs are part of the ring. Okay, so let's say that we've got this molecule. Okay, first of all, let's identify the formal charge on the carbon atom. So the Fc on carbon, we have a group 6 element minus 3 bonds. I have for the hydrogen drawn so that we can count the bonds accurately. I've also got the lone pairs, the lone pair of electrons. See, oh my goodness, I just made this mistake, and I said don't make this mistake. Carbon is a group 4 element. We don't have oxygen. My goodness. Okay, so we have group 4 element in carbon. We're going to subtract 3 bonds, and we're going to subtract 2, which is the number of lone pair or unshared electrons. It's going to give us a -1 charge. This is actually a very special negative charge. This is called a carbanion. And what we can do is we can take the lone pair of electrons and push them over to make a carbon-carbon double bond. But that will exceed the octet rule at this carbon, because if we accept a new double bond, we would have a carbon-carbon double bond kind of stretching across. Let's see, I'm trying to think about how to show this. Stretching across here, which I'll show in just a second. And we would break the octet. We would exceed the octet at the carbon I've labeled with a yellow. Okay, so I'm pushing the electrons over to this position, but I need to simultaneously push the carbon-carbon double bond electrons down to the southeast position. That's going to convert the bond into a lone pair of electrons and move that negative charge down. Now, these electrons exist in they went from the northernmost position to the southeast position. We can actually move them to the northwest position using 2 arrows again. That's going to form, and I should have 2 arrows because these are all resonance structures. That's going to form a new carbon-carbon double bond and push the lone pair of electrons up to the northwest position. Now it turns out I can keep going. I can make another bond with this lone pair, push these electrons over to make a new lone pair in the northeast position. So the electrons actually haven't been to the same spot. That is, those electrons in the lone pair haven't been to the same spot as they started. So we now have a negative charge here. Then we can push the electrons to one more new spot before returning back to the original structure. We did this exercise in organic chemistry 2, and what we illustrate with this is that resonance structures allow us to see that even though atoms within a molecule are neutral, if we have at least one with a negative charge and there's conjugation, we can roll that negative charge or that positive charge, if we need it to be, around the molecule and exist in every atom that's in conjugation. And so all resonance structures are equal. And really, that negative charge is sort of spread out across all 5 of the atoms. All resonance structures are equal. -1 charge exists to some degree. It's not like a fully negative charge, but it exists to some degree. Probably 1/5 of its typical strength on each carbon. So what we would say then is that this molecule has, as an anion, it has 6 pi electrons. It actually is using the lone pair just like our nitrogen atom and our oxygen atom use their lone pair to contribute to the pi system. If we have 6 pi electrons total, we obey Huckel's rule. The octet is satisfied, and we have an aromatic, in this case, anion. An aromatic anion. Okay, so I said we could use resonance to understand aromaticity. So this shows why that lone pair of electrons exists everywhere. We can also use it to show us acidity. So the pKa of this molecule is, well, a typical, so pKa, we're not going to do like, something in as much detail as what we would have done in quant, but a pKa for a typical carbon-hydrogen bond is about 51. Now we're going to cross that out because for this molecule, the pKa is 15. That's an enormous drop. That means that something like as strong as an alkoxide or a hydroxide is capable of deprotonating this hydrogen atom. Okay. So the pKa at this position is quite low. pKa is low. Now what that tells us is that deprotonation, or let's not get into the deep terms yet. Let's just say readily reacts with base. Now I'm not going to call this a strong acid by any means, but I'm just saying that generally if you want to let a base react with a carbon as the acid, that base has to be pretty strong, like strong enough to deprotonate something with a pKa of 51, or react with something with a pKa of 51. Here, we're saying that the base doesn't need to be as strong of a base. It could be as weak as a hydroxide or an alkoxide, which I realize is a strong base by the definitions of like aqueous Bronsted acid base stuff. But what I want to focus on instead is that the alkoxide and hydroxide can remove this hydrogen from a carbon because the conjugate base is stable. Why is it stable? Well, because it's aromatic. So when we try to remove a run-of-the-mill carbon-hydrogen bond, the molecule typically says no, because it would form something that's very unstable, a carbon anion. But if that carbon anion forms an aromatic system, so this is non-aromatic, whereas if we let some sort of base, and we used to do this reaction in organic chemistry too, we probably did it for you all. What am I thinking? We would form this, and this readily occurs, or more readily than predicted, occurs because the conjugate base is aromatic. So using resonance structures, we were able to see that the cyclopentadiene anion was aromatic. And that allowed us to see why the cyclopentadiene anion more readily reacts with a base than a typical carbon hydrogen bond would. Okay, now just to give you a sense of how strong that base is, we could look at some other pKa's. But you know what? I'll save like other acid effects and pKa effects for another lecture, and that'll be a quicker lecture. Okay, so more review to come, but that's okay. It's just getting us all warmed up and thinking about this stuff again. You can always play me at 2.5 times speed, right?